with some last minute commitments, so I was able to finish this, which is unprofessional, I'm aware of that, but I was just unable to do it. So some questions, remarks? So if this is not the case, then I'm very much looking forward to meet more people than today on Wednesday. And usually that review test is some kind of milestone which is related to the fact that we slowly start to transition to the final part of the course, which is related to the solution of some more complicated problems by computational means. Quite interestingly, actually, we now have all the ingredients which we need. So I would like to remind you that when I started this course, I was trying to explain how to construct those influence lines using the principle of virtual displacements for statically indeterminate structures. For statically indeterminate structures, the argument must be appropriately changed. But so this is one ingredient, and we spent the last few weeks trying to write the developments from structural mechanics 3 using some matrix formalism, which is advantageous at least for two reasons. One is that once you introduce those matrices, you can refer to them in a very condensed manner, which means that you save a lot of writing. And the second thing is that with a bit more modern programming languages like MATLAB or even with Python, where these advantages are not so visible, but also in Julia, for instance. Well, if you are able to describe your problem using this matrix algebra tools, then these can be solved really easily. You do not need to invest a lot of time checking the results, doing addition, solving system of linear equations, because the computer will be more than happy to do that instead of you. So what I'm trying to show today is that actually I can also do the treatment of truss structures and also the structural mechanics 3 part using the principle of virtual work, which I originally used for a different purpose. The main reason is that if I'm able to do this analysis, these derivations and explanation for truss elements or one-dimensional elasticity, if you wish, then you can actually follow exactly the same kind of logic to treat 2D elasticity parameters. Because one of the very structural or engineering interpretation of this direct stiffness method for 2D and 3D problems is that they try to map it to some equivalent truss structure and determine its properties. So what I do traditionally is that because you are now mentally preparing for the test, hopefully this will be more some kind of recap of what I did before. I'll also try to introduce some tools of trade which I will be using in the upcoming weeks, and also to try to show you once more how this can, all the developments in this course so far can be combined together to get some pretty general technique. And for that, I will derive for the third time actually the matrices which describe structural behavior of trusses, but now using the principle of virtual displacements. So what I'll try to show that through this procedure we not only recover the things which we know, meaning how the stiffness matrix of truss member looks like, but we also recover these formulas which we were using mainly during last semester when we actually took the element load and redistributed this to nodes. And also I will get rid of the final inconvenience, which is related to the fact that I don't know whether you recall that, but Martin made it also very explicit. If you actually work with this n forces, which correspond to fixed boundary conditions, you actually need to take them and transfer them to the right-hand side and change the sign. So interestingly enough, this principle of virtual work does that for you, as I'll try to show, which removes the last sign issue from the analysis, and this is something I'm really glad about. Then I will do a brief recap of the local to global coordinate transformation, just to remind you for the last but one time how from the analysis in the local coordinate system we will come to something which allows you to treat arbitrary 2D geometry and also in future to connect it with the beam-like behavior. And finally, and sorry, I was oscillating a bit how to call this exactly. At the end of the lecture, I will show you that actually what some people really do not like about this kind of method is that you are required to evaluate a lot of definite integrals, but if the formulas or stuff you are integrating are polynomials, actually Mr. Gauss was the first one to introduce a very cheap technique which gives you exact results if you take into account the polynomial order of the function you're trying to integrate and some integration scheme. So this is something I'll try to introduce because this is the last time when in the lecture I'll do some hand or symbolic calculations of integrals. This is something which allows me to make everything in the format which is very much convenient for linear algebra-like packages. So this is what I have on the menu. If you are able to understand this, then basically this two-dimensional elasticity will be just combination of these two things if I do it horizontally and vertically. Otherwise it will be very much in the same spirit. But I will do first recap of the governing equations. Then I will show you how you can take into account this beam behavior and get a frame element. And the last part of the course is dedicated to extending these arguments to analysis of load-bearing plates. So two-dimensional version of beam space. And this will be the end of the story. But through that, we will actually use these arguments over and over again. So, just to give you the working horse for all these developments, actually, everything what I have just explained and much, much more is something which can be deduced from this frame here, which is something I did my best to explain as well as possible in structural mechanics 3 course, in which I started to talk about the principles of, a principle of virtual work, which usually exists in 2 variants, and I will particularly focus from this point onward on the principle of virtual displacements. And the setup is as follows. So you basically assume that you have some isolated element taken out of the structure, as shown here. In this particular case, I'm just considering only truss elements in my analysis, meaning it's pin connected at both ends. Hence, it can it can sustain only axial loading, and hence can carry only the load which is distributed in a way that this is aligned with the element. So on the scheme left, actually this is demonstrated by the fact that I have here this XL axis, which is the local coordinate axis. Here is that vertical coordinate axis, and again I would like to remind you that this stands for local. What I have in acting as a structure is this distributed load Fx in the local coordinate system, which gives the intensity of the load. This thing actually also means that there are some internal forces acting within the element, and this is something which is traditionally denoted by N, and this internal force is the actual or normal force, whereas this is external. So this is the problem which I'm solving at the moment, plus some extra information. So this is what I have. What I would like to remind you is that actually this distributed load now, in my considerations, can be described by arbitrary function which depends on the position within this local coordinate system. I will make it more explicit in a moment. But what I mean by that is that if I would like to look what is the intensity of the distributed load, for instance, at this very cross-section in here, so the only thing which I need to do is just to have a look at the value of that corresponding function at a given cross-section of interest. And this value gives me, as I try to show by the scheme, actually the intensity of that corresponding load. So something you are hopefully pretty much used to. So again, if I just have a look at the structure here, it is loaded in the distributed manner, and this is the cross-section whose vicinity is loaded least. This one, on the other hand, is loaded most, because the intensity of the distributed load reaches its max. So is this clear, at least in this region? So this is the one thing. So we have this given distributed load intensity. I try to explain what I mean by this. It also causes some internal forces. And then I also need some additional thing which is new in this kind of methods, meaning that I know that this is some physical state in which the structure looks like, but I also now consider the virtual state, which this delta stands for, as I have used several times throughout the course. So it basically means that I will take the element in the state in which it is, in this blue state, and I imagine what would happen if that element deforms in a certain manner. And for the arguments which I will now need to develop, I will just imagine, or I will consider the situation that I know what are these virtual displacements which are associated with the stress nodes. So these are denoted as delta UA and delta UB in the local coordinate system. So I take this bar, I will assume that I somehow displace it and nodes by a certain amount, and that amount is something I demonstrate by this function. And because I know the data at the two element nodes, well, the most economic way how to extrapolate this to the level of the whole element is actually that I'm doing linear interpolation between those. So this is just a linear function, or in the terminology I'm using within the course, this is first order. Okay? So I'm assuming that everything is controlled in the way, by what is happening in the nodes or joints, if you wish, of that structure. This is because I would like to rederive the relations of the dire stiffness method. And again, this virtual displacement now is the function of the local position in here, in the same way as here. So for instance, if I decide that I will position myself in here, in this one particle cross-section, which is located in the corresponding coordinate system, the only thing which I need to do is that I will have a look at the value here. I will measure this amount, and this is the displacement which I got for this cross-section. Like at these two extremities, if I just take this value and project it horizontally, because this is horizontal displacement, I actually know that this is the amount of displacement with that corresponding cross-section just experienced. And I'm trying to be really systematic and write here all the time this XL. This is not only to highlight that actually I'm working in the local coordinate system, but also for some aesthetic reasons, so there is no other solid physical principles behind that. I will say that my local system will be actually done in a way that its origin is in the middle of the block, but this is just to make the arguments nicer. Of course, the results are independent of the choice of coordinate system, so if I just move it to, as a rigid body, then the results will be same. But just for aesthetics, this is what I have. And it actually turns out that all the things we have been developing incrementally from the very starting lecture on structural mechanics can be also, on process and particle, can be also explained by this statement. So I will say that instead of checking the equilibrium conditions between the internal and external forces, so between the normal forces and the distributed load, I can say that I imagine that my structure deforms in a certain virtual manner, and if for all kinematically admissible displacements, I have equality between the work done by internal forces and the work done by external forces, I have satisfied the equilibrium equations. So this is all what this principle of virtual work is about. It is highly, it is known for being notoriously difficult to physically imagine. Honestly, you just somehow get used to it, but it's something which is very, very handy. And here I have typo, I forgot to put this L here. And it turns out that actually I can derive orbital statics of cross structures just by assuming that my virtual displacements are linear. That these are just driven by these two values here. And that's pretty much it. So basically by believing in the principle of virtual displacements and saying that my virtual displacements look as this one, I'm able to get all the relations which I have developed so far. And this is something I would like to show you within the lecture. Okay, so this sounds promising, but it's easier said than done. So for that reason, I actually need to understand a bit better what this virtual work of internal and virtual work of external forces mean. I need to express them using the very specific format of the virtual displacements, and based on series of arguments, I can actually get the required information out of it. So what I will do is that I will start first with the work done by external forces, although I actually have written the work done by internal forces first, because this is something which, in my opinion at least, is a bit easier to explain. So I will start with this part. So once again, this is the situation in which we are now. So the only external loading for this very particle example is given by this distributed load or its intensity. So this is something which represents external loading. So this is something which will contribute to that delta W external quantity. I would like to remind you that again this delta UL is arbitrary. Is arbitrary, however, but I really do not know what went wrong. So I was charging it for an hour session. Okay, sorry. So I would like to recall that this is arbitrary linear displacement. So again, I'm assuming that actually I'm somehow moving these nodes to the right or to the left, and this is what I can do with the one which is on the left. So now, if I had some force which is acting at my structure, I can just compute force time distance it travels, and I will get some work. But this is distributed loading, so I need to make the argument a bit more sophisticated. So I would again like to remind you that here is the beginning of my coordinate system. This is my horizontal axis, and just to avoid some mismatch between the position of my cross-section and the local coordinate axis, I will draw this x for a given node, this x symbol. So before again I was I was denoting that systematically as XL, but I'm just too lazy to repeat it. So this x is variable, which tells me where I'm located, and in order to compute what is the work done by external forces, I do the standard trick of any continuum theory, and I will assume that I will take the cross-section I'm interested, and I will separate it from the rest of the structure by these two virtual cross-sections. So you have seen that many times before. This is attributed to Mr. Euler. So these are cross-sections. I will assume that this cut is of a certain length, which is denoted here as delta x, which is something non-zero but substantially smaller than the element length, which is a quantity which you can see here. And the reason why I'm doing that is twofold. So the first one is that if this length is sufficiently small, then actually I'm making negligible error in approximating this arbitrary distributed load or its intensity by constant value. as you can see here on the screen, because if I overshoot in a certain part of the structure, I will undershoot on the opposite. Or the argument might be that I will get, I can replace this curve by some equivalent tangent, for instance, and if this delta x is very small, I'm making a negligible error, and if this is straight, then this gives me the exact result. Okay? So then the only thing which I need to do, when I zoom in is that actually I will take the value of that intensity of distributed load as I see here. I can, with negligible error, replace it by something which is constant over the interval, and I can compute the resultant of this part. So this is the resultant. So I can say that this resultant f xl, and actually it should have been delta, as the value in the corresponding cross-section of this intensity, and I need to multiply it by delta x. Now, because I know what is the virtual displacement field, which is arbitrary linear buffer moment given, I can have a look at this function as I was trying to explain previously, and I can have a look what is the displacement of the corresponding cross-section, which is denoted here as delta ULX. So you can just imagine that you can read this value off from this diagram. So I'm somewhere here, let's say, so this would be the value of that virtual displacement. It would give me what is delta UA and what is delta UB. And by that construction which I discussed, I can actually take the value delta UL, which I see there, and it basically tells me that this small piece of the truss actually moved by this amount as a rigid body, because this delta x is, again, very, very small, so I can assume that it does not deform substantially. So here is my delta fx, the resultant. It was originally located here as a result of this virtual displacement of that mine experiment I'm doing. It moved by this amount. So hence I can say that this virtual work done by this small segment, delta x, can be written down as this delta fx in the local coordinate system multiplying that virtual displacement. Come on. Multiplying that virtual displacement, which I see here, so this delta UL as a function of x. Delta. Yeah, so sorry, just to, hello, just to these difficulties, I need to wait for something like 2 to 3 minutes in order to charge the pen, and I will proceed afterwards. Absolutely. Yeah, so they 1 or 2 minute break now, please. And I'll try to continue afterwards. Okay, so I was not, I was not now, so let's see how clever this idea was. So, okay, so now I will just multiply it by this amount which the cross-section traveled, and I will just see the contribution of this small piece of the structure to the work done by external forces. Okay? So again, here I have now addressed this small piece of the thickness delta x. But what I'm now interested in is not this one particle segment, but I'm interested in the contribution of all remaining ones. So what I now need to do, in order to get contributions from everything as it is plotted here, so to get the same thing, I just need to repeat this procedure over and over. So I will take the slices of the same delta x grid. For each, I will just repeat the same operation as I did here. Hence, this x becomes some arbitrary index, let's say xk. I will again assume that this delta x is same everywhere. Hence, this will become also k dependent. Here I will just take the value at xk, and I will sum over all k, so over all the slices. So if I now just explain or expand that, and just for aesthetic reasons I will swap these two contributions to have nicely working formula at the end, what I will get is that this is this delta u e at this cross section xk multiplying this resultant, but this resultant is written here. So this is fx in the local coordinate system at the cross section of the coordinate xk times delta x. And I'm just summing this contribution for the n slices. Hence, actually, this is at this moment no longer accurate. This is some approximation. So what I will do next, as you may imagine, is that I will say that now I will imagine that this n goes to infinity, hence this delta x becomes arbitrarily small. This index k becomes irrelevant, because this summation actually now became integration. And what I get as a result is that this resultant is integral of delta u at x times fxl x dx. Right? But in order to make sure that I have incorporated the whole structure, I need to check all admissible values of x's in this integration, if I assume that this n goes to infinity. So what is the lower bound on which I will integrate here? So when I'm supposed to start, this is the origin of my coordinate system. Yep. So it's minus length LA over 2 and the upper level is LA over 2. And now this is no longer an approximation, this is exactly this. So the usual explanation is, and I perhaps have used it before, is that this fx at x dx is this elementary resultant which does the work on this corresponding. But this is an alternative. If this is to be done really properly, then you need to be even a bit more formal, but I think this is sufficient. So any questions? So again, just imagine that you have some loaded bar in here, and you assume what would happen if you displace the left part by some amount, and in between you have this linear interpolation of these values. So this is something which gives you this delta u in the local coordinate system, and you will just multiply it by these two quantities. Okay? So I really did my best to explain that this is how the virtual work done by external forces works, and I will also use this argument repeatedly in two-dimensional situations. Okay, so that's it. This is hopefully the same formula, just written in much nicer way. So if there is some discrepancy, what I was, with respect to what I was trying to explain or derive before, then please let me know. But now I would like to actually recall that this fx in the local coordinate system was sketched as a known quantity, so this is something somebody gives me as an input. So in order to compute this definite integral, I also need to really now express this delta UL as a function of x, acknowledging the fact that I know the value here on the opposite side, and the fact that this is linear interpolation or first order polynomial. Okay, so what I just need to do, if this is my x variable in here, I need to write down the formula of a function whose graph is this segment. Because I know, as I have claimed earlier, that this x actually ranges from minus LE over 2 to plus LE over 2. And there are many ways how to do it, but one which is really, quite generic is attributed to Mr. Lagrange, who was one of the French geniuses of mechanics and mathematics and related stuff. And there is something which is a procedure or algorithm, if you wish, which is called Lagrange interpolation. Which is, again, something which allows you to do this polynomial interpolation based on some data at the nodes. And the procedure is not super complicated. So if I just acknowledge the fact that if I'm at the left, then actually this x coordinate is minus LE over 2, which means that I'm here. And the other value corresponds to x equal to LE over 2. I would like to make sure that actually the value of the displacement which I see here is not influenced by the value which I see on the opposite side. I would like to have those effects separate, right? So again, now the argument is that whatever happens in A cannot be influenced by what is happening in B, everything separately in a linear manner on these two parameters. So I need to write down the function, which is linear, this is what I know, and attains 0 in this particular point, where x equals to L2. So can someone help me with translating this expression into the format which will be 0 at the corresponding node? Yeah, so what I can do is just imagining that I will move it to the left, for instance. So the easiest function, if I'm a super lazy person, which vanishes at this point, or this cross-section or node, is x minus LE over 2, because if I substitute for x this particular value, this always vanishes, and this is just the first order polynomial. But this is not a full story, there is also some constant in front of that. And because I would like to having everything expressed linearly, I would also like to have this quantity appearing in the formula. So this is this delta UA. So the virtual displacement at the left cross-section in the local coordinate system. Okay? So now the only thing which remains is actually to scale this k in a way that if I take this expression and substitute for x this left value, so I need to take this expression, let's say a, and I need to make sure that if I take this a and evaluate it for x equal to minus LE over 2, I will get 1. Because if I get 1 and this particular x value, this will disappear, and I will just get the value which I searched for. Okay? So now, so I just need to orient myself. So now if I use this argument and develop it separately in here, I know that this is the value of A which I have just expressed. So I know that this is equivalent to the constant. Now instead of k, I can write minus LE over 2 plus, minus, my bad. LE over 2 and this is something which must be equal to 1. Okay? And just for aesthetics, my bad, I will say that this is Ka, and this K is perhaps not the most intelligent expression. So from this, I will immediately see that the scaling constant, which I denoted as Ka, which might bear some resemblance to stiffness. So this is why this is a stupid idea. Must be minus 1 over LE, because this is just minus 1/2 minus 1/2. This is minus L. So in order to make sure that there is 1, I just need to cancel this by this particle. And sorry for lousy writing. This is how it should. So now, you know, if you think about that, this is exactly the idea of this Lagrange interpolation. So if I am interested what is happening precisely in this cross-section, I will, or at this point, I will write a polynomial which vanishes in all remaining points if I'm interested for some reason, in polynomials of higher order. And then I substitute this original coordinate in here, take the value and normalize by it to make sure that I will get the value of 1. And that's it. So you can write it in a certain long formula, but this is just the idea. So now to move forward a bit quicker, I will also have some second scaling constant now related to this right cross-section. I need to make sure that this point does not contribute. This is his coordinates, so it's minus LE over 2. So if I now imagine that I will take this LE over 2, move it to the left-hand side, I will have 0 on the right-hand side. So this is indeed a function which vanishes at the left, and this is something which needs to be multiplied by delta u b in the local coordinate system. And if I now repeat this argument again, I need to make sure that this b at x equal to LE over 2 becomes 1, because if I'm here, I just would like to see this value. This one does not contribute by construction. So as a consequence of that, I will see that this KB LE over 2 plus LE over 2 equals to 1, and hence the second scaling constant has the same absolute value as the first one, but it has opposite sign. So instead of this contribution in here, I will equivalently see this value of minus 1 over LE. Here I will see the value of 1 over LE. So if I just do the standard manipulation, what I will eventually find out is that the first contribution is this times that, just to have the positive value first, from which I will subtract this x over LE and multiply delta UA in the local coordinate system, plus, and now I need to divide everything by the length. So this constant will come first, so this cancels out, so it will become 1/2 plus x over LE, and this is something which multiplies the virtual displacement in the local coordinate system. So this is again straightforward linear interpolation. These are the dimensionless quantities. These carry some dimension, and hence there is no mismatching. So were you able to follow my line of arguments? The argument is super straightforward. So if it looked at something involved, I did a poor job in explaining that. Or any other means are also okay. If you know from the high school, for instance, that if you just imagine that you have the value of function here is the value of x, not the one in the origin, you know that the only thing which you need to do is to take the slope of that function, and this slope is just delta UB in the local coordinate system minus delta UA in the local coordinate system scaled by the length. and now write the corresponding formula for this segment, you will get exactly the same results. In this particular discipline, people like this Lagrange approach more because it allows you to separate what is happening in selected points and interpolate it. But all options are fine. Okay? So no matter how you got your formula, this is what you get as a result. Now again written in more nicer format, and I use to my advantage this matrix relations. So now this is the time to try to take benefit of that again. So the one thing which I will do is that, because I know how matrices are multiplied, I see that this is something which can be conveniently stored in a column. So this is something I would do. And in order to get the same result as on the left-hand side, I first do sanity check, meaning that this is 2 by 1 matrix, this is 1 by 2. The multiplication goes as rows times column. So here I will see this first contribution. Here I will see 1/2 plus x over LE. And altogether I will denote this as n underscore, because this is a matrix, as a function of x. And the second thing here actually is denoted as virtual nodal displacements of the Eve element in the local coordinate system. So sorry for that. This is how the notation works. So the first one is E. This E is this E in here. The fact that I'm working still in the local coordinate system is seen in this superscript, and in order not to mix them together and get expressions which are that large, I will just combine them by separating them by comma. Okay? So any questions? So this is just straightforward matrix multiplication. The only novelty is, and this is something we have not done so far, that now these are not numbers, these are functions of the variable x, but you can formally manipulate them in the same way as the matrices, because you can always imagine that you fix your x to some given value, and if this is 0, for instance, this is 1/2 1/2, do the multiplication, get the result. So this is some vector valued function or matrix valued function in this part of this. So, it's something which is more involved but not substantial, I would say. And the main reason why I was doing that is that I now know that instead of writing in that previously derived expression this delta UL as a function of x, I know that I can write this by this compressed format, saying that this is the matrix NE as a function of x delta DE in the local coordinate system, where just in the spirit of the previous derivations, this is the matrix of so-called shape functions. And because this is at the element level, again, you can start to chain these adjectives. So this is the matrix of element, shape, or interpolation functions, because there are many of them. And this is column of virtual nodal displacements. the same object as we used before. The only thing here changes is that this is preceded by this delta, which tells me that it is not a true displacement, it is the mind game I'm playing. I have my structure, I'm assuming that I'm deforming it in that indicated way. So now what I have is the following. So if I just copy this, I will have this NE as a function of x, delta dE of the eth element in the local coordinate system, multiplying f in the local coordinate system xl as a function of x. So now if I write it in this very particular way, I will see that these two are functions of x. This first one is some given function of x depending on how my element is loaded. And this one is now also a given function of x because I have said that I will have this first order polynomial interpolation between these two. Okay? On the other hand, this thing, I do not know whether I managed to explain that or not, is a completely different beast. This is something which is x independent. This is the column of virtual displacement at the element nodes. I know exactly where they are located. This is not the distributed information, hence does not depend on x. Okay? So if I would be able to take this quantity and put it in front of this object, I can actually integrate this NE with f and get some object which I know already. Unfortunately, you cannot do this transformation, so I cannot swap this freely, because if I do that, I will multiply this column by this row and I will get something completely different. Because matrix multiplication is not commutative. So it depends, and it very much depends, what is the order in which you multiply the individual matrices. So this holds in some cases, but in general doesn't hold. And it does not hold in this case, because if I do this n times d, I will get one number. If I will do d times n, I will get matrix 2 by 2. And there is no way in the world how these two guys can be same, because they have just different dimensions. So I need some different trick. And again, this is something which presumably you have never seen before. Which if you just do this matrix algebra, it turns out that if you do the multiplication and transpose the result, meaning if you multiply the matrices and swap the rows for columns, then actually just following the rules of the matrix multiplication, it turns out that you can swap the order of those multiplications, but at the expense of actually transposing the individual components. Okay? So now if I would like to apply this to this particle product after some thought, one actually realizes that if I do the product of these two quantities, this is just one number. This is just the virtual displacement, horizontal one, which I see at a cross-section x. So if I just take one number and transpose it, it will be exactly the same amount of information. So if I now imagine that I will take the multiplication of those and transpose it, I can get this very ugly object, this virtual displacement, out of the integral. And I can further develop this argument just by saying so this 3, that was not a clever idea to do this transposition in here. So I will get this delta D virtual node displacement of the if element in the local coordinate system transposed, now taking the matrix of basis functions and E as a function of X, also transpose, multiplying Fx of the if element as a function of X dx. And what I can do now is that I can take the integral, which I should have written at the very beginning, and I can actually take this one and move it here because this is x independent. And I also separate by this operation the object which I do not like, that virtual displacement, from the things which I know. Okay? And now it turns out that if you do this multiplication, if you do this integration, because of this transposition, you will eventually compute this integral somehow. And this is something, and now, the notation becomes the most involved from everything I will present, I hope. So this F underbar EL says that this is some matrix F associated with each element and its local coordinate system, and this overbar here means that this is something which is given. So if I now do the multiplication, I will eventually find out that I'm computing the virtual displacements of the if element in the nodes, transposing it with the matrix of some forces. This is what this stands for, associated with if element and in the local coordinate system. Because this is 2 times 1, and there is transpose, this one must be of the same dimensions to have it going, so this would be a column of 2 values, and this column is column of equivalent or consistent nodal forces. Okay? And this is this is the first step of this transition from the original or previous developments of the displacement methods to the world of virtual work principles. Okay, so I know it's a lot of new information which is quite abstract. So let's just have a look at one particular example of what this stands for. Eventually, this is something which is not crazily difficult, I would say. So again, I would like to remind you that these are the 2 virtual displacements I see in the nodes. this bit is not important at the moment. So just to give you a flavor what this actually means, if I just have a look at some 8s which I was using in structural mechanics 3, if you had some element which was loaded by a distributed load aligned with the central line, and it had this particular linear intensity, these fixed end forces were given by these very expressions. So I don't know whether you recall that, but this was this landscape A4 page on which I had different columns for different ends of my element, different rows were corresponding to different types of loads, and this is something you can find here. Okay, so now let's derive this quantity in here, which is given as I have derived on the previous slide as the integral from minus it is integral from minus length of my element over 2 to the length of the element over 2. Here I have the matrix of basis functions transposed times that given intensity of the distributed load effect. So this is what I had derived before. And this is something which I multiply with the virtual displacement. I will get the virtual work done by external forces. So what I have here is exactly this formula, which is now ready for being deployed. Now I need to write down the function which describes this linear increase in the intensity of the distributed load, but I actually know how this is to be done, because the only information which I have is the intensity which is known at the right part of that cross section, and it has this intensity which is written here as F. This was the function which took care of what is happening at the right part of my interval. So what I now can do is to take this F, and just to really make it very explicit, this F, because I'm using a lot of these symbols, and I just multiply it by this 1/2 plus x over the length of the Eve element, and I just need to compute the x. So again, if you plot a graph of this function, you get exactly what you see, but not what you see here, because that would be pure 0, but the thing which you see here. So you get this function. Okay? So now you can compute this integral from minus LE over 2 to plus LE over 2. This t here is exactly the transposition I was talking about. So I now need to take this matrix, and instead of writing it in the row order, I will write it in the column order. So I will get this 1/2 minus x over LE 1/2 plus x over LE, so this is the transposition. Now I'm multiplying this by this constant f, which is the intensity of the load I will see at the end. So this is something I can throw out of the integral because this is something independent on x. And I will multiply this by 1/2 plus x over LE dx. So now this is matrix function, this is just scalar function. So the only thing which I now need to do is actually multiply by this number or this value the entries of individual matrix. And this is something I'll like to present here to continue those developments. So I will see that this is the constant which I can keep out of the integral, LE minus plus, and here I will have this multiplication I was talking about. So I will take what was originally present here, and I will just multiply it by the same function. Here I will have this dx. So again, this is this original value multiplied by this one. And likewise, I will get this 1/2 plus x over LE plus 1/2 plus x over LE, and I need to integrate this with respect to x, and again I need to do it twice because this is a matrix with just 2 rows. So now I will refresh my high school knowledge, and what I will get as a result is the following. So still I'm integrating over the same interval. Now this is a plus b times a minus b, so this is a square, and 1 square is 1/2 square is 1 over 4 minus x over LE to the second power, and here I will have 1/2 plus x over LE to the second power, because I'm multiplying using things, and dx. So this is something which I need to compute, but before doing so I will, or just to make it slightly better organized, I will just compute this integral. So this is 1 over 4 minus x square over LE square dx, and these are the bounds. So now I use the calculus 1 arguments to find out that the primitive function to the function which is here is x over 4 minus x to the third power over 3 LE to the second power, and I need just to take the top bound, substitute it inside, and subtract from it the value in the bottom. So this is something I will do. So what I will get at the end is the following. So for the top or upper bound, I'm getting this LE over 8 here I have minus, and here I will have LE to the third power over 3
times 8, because this L over 2 to the third power gives me precisely this, times LE squared, sorry, there are two parentheses, so I know that I can cancel this out, and this is 1 over 24. So this is this first part, or the first contribution, if you wish, from which I will subtract the second one. So I will have this minus LE over 8. And now, because this is even function, then actually I will see that this will have the same value as here, but with the opposite sign. So I will just see that here I will have minus minus plus LE over 3 times 8. But if you just compare it, what is written here, this is precisely the same thing as here. So this is, the result is actually 2 times, because again this is same as this one. So this is 2 times, and now I will say that this is 3 times 8. So here I will have 3 minus 1. And this is to be multiplied by LE. I'm almost there, because if you just do your algebra, this is 2. 2 times 2 is 4, divided by 8 is 2. So what I will get as a result is 1 over 6 LE. So a lot of computation for relatively straightforward result. Okay, so who is enjoying these types of calculations? I do, but I'm usually the only one in the audience. So of course, I just wanted to show it to you once, only once, just to make sure that you recall that these are operations you have been taught. What will happen in the future, nobody knows, as far as I can tell. But what I get as a result is this function f. Here this is multiplying LE over 6, and this is the result, right? So now I will not torture you with performing the tedious computation again. If you just have a look at these handouts, which I will make available after the lecture, you can just later see some very small script which does that, or you can use Wolfram Alpha or whatever you prefer, but you can actually do the precisely same stuff in here. So this is MATLAB based. It tells you that I have 3 symbols, XFL, and hopefully at this stage of the course the syntax is self-explanatory. So in that I was cheating a bit, or made you available. Or you can ask ChatGPT to compute that for you. But I have been recently made aware of the fact that if you ask this huge model to perform such trivial operation, you are wasting a lot of energy, so better to use something a bit more specialized. But if you are not so concerned about your energy consumption, then I'm pretty sure that ChatGPT would be more than happy to compute that instead of you. Okay, so now if I do so, I can use this MATLAB knowledge, which will give me these values. And the reason why I'm actually doing that is that I will just copy the result here. Okay? So
calculation which you need to do in order to get the quantities which correspond to this equivalent local forces. That they are equivalent to the distributed load, and they are equivalent with respect to the principle of virtual work, or the work done by external forces. So this is what you get as an outcome. Now, if you actually recall what was the original assignment, then it turns out that this is the value XAB local, this is the value XBA local, but with the opposite sign. So just to make connection to structural mechanics 3, this is minus XBA local, and this is minus, AB and BA. These are the guys from structural mechanics 3. And I would again like to remind you that there was over bar, and these were also fixed end forces, if you recall, which you then took and translated to the right hand side. So this is something you do not need to do here, because these are the forces which act as nodes. So the principle of virtual work does this bookkeeping of signs, which is very nice of that principle. Okay. So if I now am to try to explain what I get as a result, and this is to be highlighted, I'm saying that instead of computing the virtual work done by this distributed load, I can equally well do the following. I can take these distributed forces and transfer them to this F times L over 6, F times L over 3, resultants. If you sum these two and determine the resultant of the distributed load, you will get exactly the same value, so this is why this is called equivalent. And these two forces, they have this very particular property that if those are used with the corresponding virtual displacements, they perform exactly the same work as the distributed load. So instead of computing this integral, which I have done before, the only thing which you need to do is to prepare this 2-by-1 matrix, pick some particular values of this arbitrary displacements, or take them as parameters, and do multiplication here plus multiplication there. So this is why these are called equivalent local forces, and again, from the perspective of the virtual work done, this cannot be distinguished from that. If you assume that the displacements in between those two extreme points, they are interpolating linear. Okay? I have exhausted my time for today. Okay, so I would like to close the session. I was slow, perhaps too slow, but I really did my best to explain to you how this principle of virtual work does. And what I was trying to show to you is that this one and the only one formula here actually allows you to compute all n forces you have in the table. The only thing which you need to do is just to express how this distributed load looks like and perform the integration, which you even do not need to do by hand. This is something you can do on a computer. And eventually you don't need to do it because you have these expressions already, so you just need to change the sign in all of them, and you have your results.
So what is waiting for us next week is that I'll try to develop the same argument for the work done by internal forces, and then show how this gives rise to the stiffness matrix of my element, and do a brief recap and move to two-dimensional elasticity after. Yeah, so thank you very much for your kind attention.